Can everyone hear me? Cool. Welcome everyone. My name is DANNY CRANMER. I'm a Apache Flink committer and PMC, and I'm a principal engineer at Amazon Web Services, working on managed service for Apache Flink. Before I jump into the talk, I want to give a small background story. So I've been a long-term attendee of DevOps. I'm a Java developer through and through. I started working on Flink 4 years ago, and it was completely new to me, like Java framework. I love Java, hadn't heard of it. So I want to advocate Flink because it's great. I love it. I submitted a talk last year, didn't get in. So this year I submitted 4 talks, got 3. So if you want to learn more about Flink, there's going to be some other ones from me. So in this talk, we're going to set some background, like batch and stream processing. What is Flink? What is it used for? And how does it actually work? And I'll put some demos along the way. So going to the start, let's talk about data. So organically, data is a stream. We don't, or we rarely have just one big lump of data that doesn't evolve over time or grow over time. So organically, data is a stream, and you can usually assign a timestamp to it, and it can usually, you get more data over time. Data can include sort of fraud detection data, so looking at IP addresses, bank transactions, etc. Shopping information, placing orders, adding to cart, stock market information, click data, advertisement data, or any KPI revenue, sorry, any KPI monitoring. So anything with a timestamp is what we're interested in here. When we think about data and time, there's a few different concepts to get your head around. So firstly, we have now. So the line on the right is now. This is where we are now. Everything in front of it is the future. This is new, fresh data that we're going to get later. So that's great. And in the past, we have historical data, and then we have a backlog. So the backlog is the difference between where we're processing data from until now. So if I'm processing data 2 minutes in the past, I have a 2-minute backlog, and my lag is 2 minutes. And certain storage systems, such as Kafka or Kinesis streams, have these lags and millis behind latest metrics as first-class citizens and concepts. So batch processing, start with batch processing. It's easy to understand. We run a job on a fixed, usually on a fixed interval. It doesn't have to be. For example, we run it every 30 minutes, and we process a batch of data. And typically, these are you have all the data you have all the data, so you can put all of it in memory. You can run all the processing over it, and you can produce an output. So it's quite simple. Compare that to streaming. We continuously consume data. We continuously compute some result, and then we continuously output data. So this is one of the key differences between streaming and batching. And there's going to be a theme around latency here, because it's one of the selling points of stream processing. So I'm going to give you an example of what end-to-end latency is, what it means. So this is quite an easy example to understand. So I'm sure we all watch video streaming services such as Prime Video or Netflix or any of them. So in this scenario, we have someone who's watching Prime, and they may have watched a program and they click, yes, I like that. And when they click like, that gets sent to the cloud. It goes through some recommendations engine, which says, oh, you like this, so you probably like this as well. And then it sends the result back to the user. If that result takes an hour, 2 hours a day, then that's less useful, right? Because they're in that mindset. They might want a new recommendation straight away. So the quicker we can complete that round time loop is better. And this is what we call end-to-end latency. So the time it takes from the data to be created to the processed output to actually be delivered to the destination and materialize like business value. And so when we compare latency between batch and stream processing, we can see in stream processing, the time between the creation of data to the output of results is very small. We call it near real time because there are delays, small delays in network and storage and things like that. Compared to batch, when we process data in batches, I say worst case, but there's obviously, it's going to be worse than that because there's other delays, like near worst case. But the size of your batch determines sort of the biggest latency that you are prepared to accept. So in this case, we're processing batches in every half an hour, so we get results every half an hour. So that means we're happy to have stale data that's half an hour old. And there are many graphs that demonstrate this that you can find on the internet, but particularly like this one because it shows the 4 stages, and I've stolen it from there if you want to look at the original post. So essentially the idea is that the business value decreases over the time to action. So you have an event that you're monitoring, that you capture, or the actual event, then you capture the event, then you analyze the event, and then you take action. And the more you can reduce that, the more value you can get for your business. Obviously, it depends on the use case. You might not need to have a fast turnaround, in which case you may be okay with batch processing. But there are more and more use cases arising, more and more competition that mean businesses want to act faster. So we need tools and frameworks that can allow us to make these, take these actions as quickly as possible. And this is obviously what Flink is going to try to do. And as a summary, I'm now going to maybe make streaming not look quite so good. But when we look at batch versus streaming on some sort of key topics like latency, yeah, generally speaking, latency is higher in batch processing, it's lower in stream processing. Complexity is lower in batch. Because we have everything in memory, we can write a very simple function that then just computes some output, simple. But for streaming, we have continuously updating, so we're continuously computing some result. So there's more complexity around that. Like we need to store the intermediate state, we need to handle the scaling. Typically, batch processing is scaled vertically. So like I'm running a batch job, I'm running out of memory, more memory, it passed, cool. It's not a problem anymore. With streaming, we typically scale it horizontally, which is inherently more complex. Because of that, and because streaming typically runs all the time, the cost of batch is usually lower because I can run a job every half an hour, like some lower compute costs. Streaming is running continuously, so typically it has a higher cost. And performance is typically higher in batch as well, because you can optimize your functions to, say if you're computing, you don't need to store the intermediate values, so you can be CPU bound and produce outputs quicker. So it all comes back to latency and the business value out of that and the trade-off you want to take on these things in order to achieve your needs. So let's go into what is Apache Flink. I always like to quote the phrase from the website because once you read this, you understand what Flink is. So I'll read it out just in case it's not clear. So Apache Flink is a framework and distributed processing engine for stateful computations over unbounded and bounded data streams. Flink has been designed to run in all common cluster environments, perform computations at in-memory speed and at any scale. So you all know what Flink is now, and you can go away and you can use it, and that is great. So no, you can't. And actually, this was one of the hurdles I had. You look at the docs, and it's a paradigm shift in programming, moving to stream processing. So I'm going to try and break that down and help you understand what it is, and then we'll use it. So one of the phrases in there, Apache Flink is a framework. So that means for us, on the left, it supports various languages. So we can write data analytics jobs in Scala, SQL, Java, Python, or any other JVM language. And then the actual APIs we invoke from these languages, there are various layers. So we have at the top end, we have SQL. We then have a table API, which is more like a statement set type, if you're familiar with Hibernate. Then we have a data stream data set API, and this is where Flink gives you some Java operators, similar to a Java 8 stream, where you might filter, map, print, for example. It gives you them sort of operators. And then at the bottom level, you have a process function, which is just a callback, and you implement a class and you do all the work. And obviously with this, you have control and abstraction. So if you go to the top, you have less control, higher abstraction. You may find, oh, I can't do exactly what I need, so I need to move down the stack. So that's a standard trade-off with any programming. In terms of what Flink can do, here are some of the common operators. So query. So when we say query, it's usually a continuous query. It could be a batch query, but so like, for example, I'm reading data from a stream. I want to change the case of some string, like to uppercase, and I want to output some results. So that would be a continuous query that runs indefinitely. I can window, so I can aggregate data, reduce data in windows, or create, run arbitrary computations over windows of data. Filter, transform, aggregate, so multiple records into one. And then join. Join is a really powerful thing. So we may have data in Kafka, data in MySQL, and we want to merge it together. So Flink allows you to do that. Join data from all sorts of different sources. Distributed processing engine. So Flink is, when we use Flink, we create a Flink cluster, which consists of job managers and task managers. The job manager is the coordinator, and then the task managers are the worker nodes. So when we say it scales horizontally, this is how we scale. We add more task managers to scale out horizontally. Now I'll talk a bit about scaling a bit later on. But essentially, we spin up a cluster and we deploy our jobs to this cluster. Bounded and unbounded. So this is one of the places where Flink shines. It's that the actual query you write is agnostic of the data source. So if I write a query that analyzes data, Flink doesn't care if this data comes from a batch source or a streaming source. So it could come from MySQL or it could come from Kafka. You can write the same computation logic and run it against both of these sources, and then Flink will run the queries and it will give you the same results, assuming you've done it properly. But essentially a unified API for data querying. Next one, so stateful. So Flink is stateful, and as a long-term DevOps attendee, like everything has been, oh, we should design stateless systems. We don't like state, which is true. But when we want low latency, stateless systems are not so good because we say stateless, but they usually call some database. So we're adding some network latency. So what Flink does is it runs everything in memory or as close, so it runs statefully. All the state is held in memory or in disk. So when I say statefully, let's say we're computing a rolling average. So when we get a new record, we need to know what the current total and the count is in order to compute the new average. So them two numbers are going to be available to the operator running the code in memory, so we don't have any delays trying to fetch them from a database or a cache or anything. So this is why we say it's in-memory speed. But of course, the problem with stateful is when it blows up, it's not fun. So to tackle that, Flink has built-in fault tolerance. So it has checkpointing, save pointing, so that when your job dies, we can automatically restore from a latest checkpoint, continue processing. And then we also have semantics for exactly once processing, which means we'll only process each record exactly once, so the output will be correct and consistent. There are some caveats around syncs. So if I'm writing my data, there may be some duplicates at the sync, but there are also ways to tackle that with two-phase commit, like transactional writes. But the point is that the output is consistently correct, and we typically recommend you design for idempotency because writing transactional writes are inherently more difficult. They come with extra latency, etc. I won't go into that now. Okay, at any scale, so I've spoke a bit about how it scales, but there's some quotes from the website. I'm not sure exactly where they come from, so but trillions of events per day, terabytes of state, and running on thousands of cores. So it scales out to huge applications. Okay, let's move on to some common use cases, and I'll jump into a demo to stop talking at you. So if you look at any Flink docs, you see these three pillars of use cases. We have event-driven applications, stream and batch analytics, and pipeline and ETL. Let's start with pipeline and ETL because that's simple. We want to move data. On the way, we might transform it. So we may, typical like modern use cases, I want to dump all my data into a data lake. Flink can do that. So you can say add a CDC, change data capture onto a MySQL database, pump it through Flink, convert it, enrich it, and then dump it in a data lake. Flink can do that for you. It can also call out to machine like ML models and things on the way. So that's quite simple. When we talk about event-driven and stream and batch, the way I like to think about it is that what's the difference in the output. So an event-driven application would typically monitor loads of inputs, and it would generate an action. It would take an action when some condition is met, like fraud detection. If we're monitoring credit card transactions and we see some fraudulent behavior, we may block the card. So that was what I would consider an event-driven application, whereas stream and batch analytics also monitors from a range of sources, but the output is more business intelligence or information that you can then use to drive downstream processes. It doesn't generate an action, it generates information, more data that then can be processed downstream. But there's a few typical use cases there. Okay, now let's look at an example and I'll show you how it actually works. So in this example, we're going to do a simple, I guess it's ETL type example. So we're going to spin up a Kafka cluster with two topics, source data and redacted data. We're going to push through some order data. You can see there that this order data unfortunately has credit card numbers, so we want to just redact that data. So we're going to just replace it with a bunch of asterisks and write it into the destination Kafka topic. So I'm not Josh Long, so I can't type all this as I go. So I'm going to have to resort to more traditional copy and paste. And I'm starting from scratch here. So I'm going to actually start up Kafka. So some commands I copied from their website that are going to spin up Kafka. Oh, sorry, I did this last time. There we go. So Kafka is running. Now I'm going to copy a couple of commands to create these two topics. So we're creating the orders topic and we're redacted orders topic. And just to show you that there's nothing running on this port. So Flink is not running yet. So I'm going to start the Flink cluster. Probably could have typed that one to be fair, and it's not even right. So start cluster. So I've just downloaded the distribution of Flink from the website. The only change I've made is there's a Flink config file, and I've just changed this line here. You see number of task slots is 8, which I'll show you what that means in a second. But besides that, this is a vanilla off-the-shelf Flink distribution. So if I now go to the local host, the browser, this is a Flink dashboard. So the job manager, the coordinator, as I showed earlier, this UI is hosted from there. So this is not some additional tool you need to install. You get this out of the box. And I didn't write it, so I can say this is fantastic. And while operating Flink, it's been super helpful. But it shows me a lot of information. So there are 8 task slots, as I edited in the config. There are no running jobs. If I go on the task managers list, we can see we have 1 task manager connected, and it has 8 slots, and all of them are free. So what I'm going to do now is run another command that's going to spin up some prerequisite jobs for my demo that are their SQL jobs. They're going to run up and exit. I'm not going to talk too much about them because all they are doing is populating some dummy data into the Kafka topic. So if I just flip back to here, if you remember, we have this source topic which has some user order data. So this data is now being generated and sent to Kafka by Flink. On the Flink dashboard, you can see there's now a running job. And if I click on it, it will have a simple job graph which shows source, orders, data gen, and then it writes into this orders topic. So to continue the demo, I'm now going to jump into the SQL client. So this is one of the options of writing Flink jobs is SQL, and SQL client is one way of generating the jobs. This is not typically used for production. This is more of like a local development tool. It has some nice ASCII art. Now I can just run SQL queries. No, I can't. I need to paste the schema in. So this is SQL, so we work on tables. So the orders table I'm creating here, the top block is the schema, maps to the JSON I just showed you, and then we have this with block which tells Flink where the source of this data is. You can connect with schema registries, etc. Here I'm just using like local schema, local catalog within Flink. So we basically say we're reading from Kafka, the topic is the orders topic, the bootstrap server is localhost, we're reading from latest, so this is sort of standard stuff, right? If I create this table in Flink, and now I run a select star from orders, we'll see the data this is going to start reading from Kafka, and it will start dumping some data into here, hopefully. Yep, so here we go. I can't actually see it all. That might be a problem. Might need to zoom out. There we go. And just to show you, if I jump back to Flink, we've now got 2 jobs running. Because it's SQL, the naming's not very nice. If you use Java, you can put nice names, but it just moved as I clicked it. That's helpful. But this is a very simple job. It's optimized into a single operator, which I'll talk about in a bit. So it's source orders and sync to the SQL output. So we can see the results here. Anyway, so moving on, what we need to do is redact that credit card number, right? So in order to do that, I need to create a new table for the destination topic. So this one is the redacted orders table. So it's very similar, apart from it's the topic, the Kafka topic is now redacted orders. So I'm going to create this table, and then I'm going to run a very simple SQL query, which is a continuous job. So insert into redacted orders, select the 4 fields, and then just the asterisks that we wanted. Sorry if that's a bit small, from the orders table. So if I run that query, so this query is now running on Flink. I can show you that. We now have this one that's been 3 seconds old. Again, it's a very small job. Source calc is the map to insert the asterisks, and then the writer and the committer is the sync. So cool. This is now a streaming job that's going to run forever until we kill it. It's continuously streaming data from Kafka and writing it into the redacted topic. And if I now show you the result, select star from redact, I'm going to use autocomplete and it will do that for me. We'll now see that hopefully the credit card information has now been redacted. So cool. Obviously that is a very simple example. Yeah, I think it should be finished. Let me just make sure that's closed. Yep, there, that's good. Okay, let's get back to the slides. So that was our first use case example. I'll have another one a bit later on. So the point of this talk, how does Flink actually work? So hopefully you all know like why, what, but how. Let's go through the how. So the first step is as a programmer, as a data scientist, we need to define a processing pipeline using the Flink APIs. So as we just covered, you can use Scala, SQL, Java, Python. We just went through a demo of SQL. So we used a SQL query to generate this. Just to recap, on the left is our table, and we have the schema at the top and the connector at the bottom. You can see connector is Kafka. There are a range of connectors you can use. Actually, my next talk is about connectors if you're more interested in connectors. But this is just key value properties that get passed to the connector constructor. And you can also create your own connectors. Then on the right, we have our query. And Flink takes this information. Actually, I won't say that yet. Next slide is Java. So equivalent Java looks like a lot, but it's actually very simple. Like the top 2 blocks, the top 2 builders are creating the source and the sync. So we have a Kafka source, which is set in the location, a serializer and deserializer. And then the actual job is at the bottom there. We can see it's, I like to think it's similar to Java Streams API, maybe why I liked it, but we say environment from source, we say from the Kafka source, then we're going to map, simple map function, we're going to create a new builder and change the credit card number, and then we're going to sync it to the Kafka sync. So very simple, very nice to use as a Java developer. So Flink takes that Java code, that SQL code, it will run it or interpret it, and it will generate a job graph or a logical graph. So this is a logical chain of operators that define how data flows. We can read it from left to right. This doesn't represent the one I just showed, by the way. I just wanted to add a join. So in this case, we've got 2 sources. One of them is being mapped, so transformed. Then we're going to join data. So it could be orders with user information. You could be looking that up from a relational database, or it could be another Kafka topic, for example. And then in this case, we have a sync. So these are called operators. So the next step is the job graph is the logical graph. Now we need a physical chart. So how do we actually run this? How do we actually deploy this to our compute? And this is where I want to touch on parallelism. So I've said Flink is scalable, and I said you can scale workers, but actually we can scale the independent operators of a job graph. So in this simple example, we have a source, account, and a sink. And we've set different parallelisms on the source, account, and the sink. So if we have a particularly heavy compute function in the middle there, we may want to scale that bit horizontally, but keep the other bits like single tasked to reduce our compute costs. So in this case, we've done that. We've got 2 parallelism on the source, 2 parallelism on the count, and then the sink is 1 parallelism. And the execution graph there shows that. You can think of each of these circles as a thread, basically. So in Java, you're going to have 5 threads. There's some caveats, but 5 threads. We call these subtasks. Data flows from left to right. And I'm also going to quickly touch upon this key by thing. So Flink handles network shuffle for you. So the way data flows between nodes, you can either use a key by, where let's say we have 2 downstream nodes and we have a key space from 0 to 10, and we want to send half of them numbers to one node and half to the other one. So like a consistent hashing type mechanism to distribute data. So Flink does that for you. And Flink can also reorder data as well. So there was a talk yesterday about Kafka, and the general advice is to try and keep all the keys in the same partition. But you don't you can use Flink to reorder or regroup by key. So it doesn't, in this case, it doesn't matter if the sources have the keys in the same topics or partitions. They can be reshuffled by Flink. But then you lose ordering, of course, because the arrival times might differ. And there are various strategies here. So key by, rebalance, which is round robin, forward. There are various strategies you can use there. So how does data actually flow between the operators? I said that the operators are basically threads, and I said caveat because that was a lie, and here's why. So here we can see we've got just 2 threads, but we've got 4 operators. So Flink will optimize your job graph to reduce network calls. There are some trade-offs to be made there, which you can read about. But when we have an edge that makes a network call, we have network buffers, and then we have a TCP call in the middle. And this is how Flink implements back pressure. So this means if the source is trying to write into this network buffer and there's no space because the downstream operators have not consumed this data yet, then the source thread will block there, which is back pressure, right? Because the downstream operators are moving more slowly than the source, and they're saying, hey, wait, you need to wait. I need to process this data, and then you can send me more. When Flink optimizes, it will put multiple operators into a single thread, and it will be direct method invocation. So it won't go over the network, it will be direct method invocation. And that obviously depends on your previous slide. If you use a key by, we can't do that because we send data downstream based on which key it is. But if there's a forward call where it always sends it to the same, like subtask 1 goes to subtask 1, subtask 2 goes to subtask 2, then we can chain these together and we can remove some of that network. Deployment. So I spoke about task managers being workers. Task managers have slots. This is how we scale out Flink jobs. So we add more slots. A task manager can have n slots. And we deploy we deploy parallel slices of the job graph to a single slot. So here you can see our parallelism of the job, or our maximum parallelism of the job is 2 in this case. So we'll need 2 slots. And each slot is going to contain one of these parallel slices. These parallel slices, or these slots, are then deployed to task managers. So just to illustrate that it's quite flexible how you do this, on the left we've got a single task manager with 2 slots. You can see the job is deployed to them 2 slots. And on the right we've actually got 3 task managers. Each of them has got 1 slot, and task manager 1 has taken the 1 vertical slice, and task manager 2 has taken the other vertical slice. And the third one is idle. You can then submit more jobs. So this is how you scale Flink. You have task managers, slots, and parallelism. All these things together is flexibility. Okay, once you deploy the job, then it it enters this huge state machine. I'm not going to go into details. I wanted to illustrate. On the left, we have a job lifecycle. So when I submit a job, it goes from creating to running. And then each of them subtasks has their own state as well. And they also go through this lifecycle. So just to illustrate that, I'm not going to go into any more detail. Kafka. So common question I get asked when talking about Flink and Kafka is how the partitions map to the subtasks, because the people tend to think, oh, we need one subtask per partition. But no, that's not true. In this case, we've got a source, a Kafka source, with a parallelism of 2, and we've got 5 Kafka partitions. So Flink has a coordinator in the source, which decides, it basically lists all the partitions to work out how many partitions there are. And then it will say, I have 2 source readers, so you are going to process partition 1 and 2, and you are going to process partition 2, 3, 4, and 5. And that logic is managed by Flink. So you can scale these things out independently, and Flink will handle that for you. In fact, a good example of this is the Kinesis data streams connector, because you can dynamically change the number of shards. So in Kafka, the partitions are usually fairly static, but in Kinesis, the shards constantly change, and Flink will automatically reassign shards to readers dynamically for you, and it manages all of that. Okay, we're going to look at a second use case now, which is a common use case, which is a tumbling window. So in this case, I'm going to just reuse the data that's still running on my Flink cluster, and we're going to say I just want to count the total value of orders by each user in each window. So for example, this is not showing that actually, but the first window here, we have 4 records, so we're going to produce 4. The second window, we have 5, so we output 5. So Flink has support for various types of windows, so tumbling, sliding, session, which you can go and look at. I'm not going to go through them now. But one of the key concepts of Flink here is event time. So there are different time semantics of Flink, and if you went to Hong's talk yesterday, he went into more detail about this. But essentially, when Flink processes, it understands the event time of the record, so when it was actually created, not when it's arrived at Flink, not when it's processing it, and which is very powerful, because if we run the same job against the same data, it doesn't matter if you're processing a huge backlog or you're processing it on the fly, you'll get the same outputs. Okay, so how do we do this in SQL? I'm actually going to demo it in Java, but I thought I'd show SQL. So report the total spend every 1 minute. So in this case, we're selecting the window start and end just to show the timestamps. And then we've got user ID, the sum of the price, as we said before. So the interesting bit is the next line. So we're going to, from table, we're going to tumble the orders table over the order time. So this is the column in the table, the timestamp column, the event time column, and the interval is 1 minute. So this is basically create a tumbling window of 1 minute. And then we're grouping by the window and the user. I don't know if my explanation of that really helped, because I just kind of read it out, but hopefully it makes sense. But let's look at it in Java, because we all love Java. So this is you can actually see it this time. I know I can use the tools thing, the actions, but it usually crashes. Anyway, so this is a single class Flink job, generic name. This is our model, called it order. I'm using Lombok. So we've got the fields that appear in the JSON, user ID, order ID, total price, order time. Let's not talk about the timestamp format here. The credit card. And then here's our job. So this looks kind of similar to the example I showed you earlier. Firstly, we set up the stream execution environment. So this basically gets a handle to Flink. It's a static call, gives you the environment, and then you start building up your job graph from there. Setting the parallelism to 1 just for simplicity here. So we're defining a source, Kafka topic, Bootstrap server, where to read from, standard stuff, JSON serializer. You can use arbitrary formats here. So out of the box, Flink supports JSON, CSV, Parquet, Avro, but you can implement anything you like. We're then defining a watermark strategy. I'm not going to go into watermarks too much. Again, Hong covered that. It's basically the way Flink handles late data, out of order data, so that if you read data, it doesn't matter if a device goes offline and it sends data a few minutes late, Flink can reorder that for you and you could get the same output. And finally, the actual job. So we're reading from Kafka source, key by user ID. So this is the group by in the SQL. And we're going to dot window tumbling event of 5 seconds. I've done 5 seconds for the purpose of the demo, so we don't have to wait a minute for results to appear. And then the output is the sum of the total price, and then I'm just mapping it to a nicer string, and then print. So print is just going to print it to the terminal. env.execute would run the job. And earlier I said in Java you can add a nice name, so here you can add a nice job name if you like. So as a Java developer, I may want to build this, generate a jar, and deploy it to a cluster. That's typically how you would do it in production, but as a developer in my IDE, I can just run this. Flink will spin up a mini cluster, everything in memory, and you can run it all in memory within here. So we don't need to worry about spinning up Flink clusters. So I'm just going to run application. This is going to start consuming from the orders topic. I've disabled log4j so we don't get all the other outputs. So every 5 seconds, we are going to get the output, which is the total order value for each user. It's worth noting that I limited the number of users to 6. I tried to do it to 5, but the end is inclusive. So remember that if you use Flink. There we go. So quite simple, right? Cool. So let's jump back to here, and we're going to finish up by talking about like what actually happens under the hood for that job. So we've got a job graph, a tumbling window, which is doing what we just saw. So on the left here, I'm showing 2 parallelism to illustrate the key reshuffling. So we're assuming we've got a key space of 6. So 1, 2, 3, 4, 5, 6. The input events similar to what we saw. So in this case, we've received an event. The user ID is 3. We're keying by user ID. So this record is going to flow across the top line into the top operator. Flink sees that the time is 1, and it tries to assign that to a window. So we don't have a window at the moment, so we're going to create a new one. Flink aligns the time to the time boundary. So in this case, we've got window from 0 to 4 because our window size is 5, and it puts that into the window. So user ID 3, total order value is 5. Very simple. Now we receive another event. This time it's for user ID 2. User ID 2 happens to fall across the top edge again because of the key mapping. And now we update our window state. So we now have user ID 2 has total price of 9. We receive another message. This time it comes in on the subtask on the bottom. Again, it's for user ID 3, which means it heads up to the top one again because of the key space. In this case, we already have an entry for user ID 3, which was 5, and this is the total price is 12, so we add 5 and 12 to get 17. Yes, that was right. So the next case, we receive a new record. So in this case, the time is now 6, and if you remember, our time window is T0 to T4. So because the time has now progressed past the window, we're going to close that window, we're going to generate the result, and we're going to output it. So that is, this is basically called a trigger, where we trigger the window close and trigger the computation. And you can do anything you want here. You can write arbitrary Java code. In this case, we're just outputting the sum. So you can see its output there. Because this order type is 6 and the user ID is 5, the record flows to the bottom line, and it's generated a new window in this operator. You can have windows open in parallel. You could have, if you allow, say for example, if I allow 10 time units of late data, you could have multiple windows open side by side. But I try to keep it simple to illustrate how that works under the hood. And when we talk about stateful processing, the contents of this window are stored in this Flink state, which is then backed up by memory or spills to disk. And then the checkpoints and snapshots are then persisted in like persistent storage, usually something like S3 or blob storage. Okay, and that is it from me. I finished a bit early, so we have time for questions. So does anyone have any questions? Where?
One question is on this order window program, when we are calculating the total price, it was shown as a field. Is it possible to use order dot get total price, or it's API is just based on fields?
Sorry, I'll open the Java code. So in this one, the question was, is it possible to, this is shown as a field, is it possible to, so the sum is a built-in operator, and this accepts a position or a field. If you wanted to, you can add arbitrary methods in here. If you wanted to calculate that yourself, I think you would use an accumulator. Or aggregate, is it aggregate? And then you can have an aggregate function where it's basically like a reduce where you can aggregate multiple together, and then you can implement that however you want. Flink is very flexible. So generally we have a higher level of abstraction, and then you can go down the stack and create your own windows. So this is an example of a higher level API where it's less flexible. And then if you want more flexibility, you can go and then implement your own like aggregate functions, etc. But yes, you can do that. Hello.
My question is more related with the scalability. You mentioned that you need to partition data by key. So does Flink provide support, or you need to do by your own? I mean, imagine that you add a third worker or whatever, then somehow you need to split the workload between three. So
Yep.
is this done automatically by Flink? Or you need to...
Yeah, so the question is, when we scale, how does the state scale? I guess this is a good slide to talk about this. So, right, so in this case, we have parallelism of 2 in the middle operator, and we have 6 keys. So this adds up quite nicely. If I were to change the parallelism of 2 to 3, what Flink would do is it would take a checkpoint or a save point, which is a snapshot of the state. It would then increase the parallelism, and it would basically restart these 3 operators from the checkpoint, and it would redistribute the state. So it would say, for example, keys 1 and 2 could go to subtask 1, 3 and 4 to the middle one, and then 5 and 6 to the bottom. And then from then on, the records would flow to the correct downstream operator. Yeah. So there is, you've touched upon one thing there. When you scale, there is a bit of downtime because that process takes some time. So it's not like zero downtime. There are ways to do that, like blue-green deployments, etc. But yeah. Where does it save the state? So there's 2 concepts of state. So we have in-flight state. So when the app's running, the state that's being used, we have something called a state backend. So these are configurable, but out of the box, Flink gives you a in-memory state backend, which is basically a hash map, which is great. It's fast. It doesn't need to serialize and deserialize, but obviously you're limited by the memory of the node or the JVM process. You then have a RocksDB state backend, which most of the state hopefully resides in memory, but it's native RocksDB memory, but it does spill to disk if you then go over. And then there are you can implement your own arbitrary state backends. So that's in-flight state. So when I receive a new record, I need this information. It pulls it from there. When you take a checkpoint or a save point, it essentially takes a dump of that state backend and it will persist it in S3 or anywhere. Yeah. I think you won that one.
Is there support for Kafka headers still?
Kafka headers.
So in Kafka streams, you have some access to the headers in terms of being able to route.
I think I'm not entirely sure, but I think where in a source you supply a deserialization schema, and generically you just say, I want to convert it to JSON or CSV, but there is like a Kafka deserialization schema, which I think gives you access to the Kafka metadata. So if you wanted to access the Kafka headers, I believe you would need to provide a custom Kafka deserializer. So in here you can see I'm using a value only deserializer, but I think there's a Kafka record deserializer, and this would give you access to the Kafka metadata. But I'm not sure exactly what metadata, but I'm sure it would give you the headers. Yeah.
So in your example, you use Kafka's source.
Yep.
So the same thing can be done with Kafka streams. So pros and cons to use Flink instead of Kafka streams or vice versa.
Yeah. I wouldn't say I'm an expert in Kafka streams, but one of the biggest things is that Kafka streams is very much coupled to Kafka, whereas Flink is agnostic to the source and destination. Like if you want to go, Kafka streams is great if you want to go from Kafka to Kafka, but if you want to do that, if you want to go anywhere else, you have to hop through Kafka with Kafka streams. I'm generally speaking, I think Flink is becoming a de facto standard for stream processing. It's even being, I don't know if you're following, like the Confluent of backing Flink heavily now. So it's a 10-year-old project, but it's growing very rapidly now. So I think it's the technical details. Sorry, I can't give you a good explanation, but I think Flink is the sort of de facto standard for stream processing at the moment. Yes.
Also, when would you choose Flink over Spark?
Spark. So I'm not saying you should choose Flink. Obviously, pick the tool that's right for you. But generally speaking, Flink is considered to be faster than Spark because it deals with individual records. Spark is micro batching. So it's a batch framework that you can run streaming jobs on, whereas Flink is a streaming engine from the ground up. So it's been designed for streaming. And generally speaking, it's faster. I think the APIs are more expressive for stream processing. But again, I don't have a concrete, I don't have an exhaustive comparison. Exactly. I think they say that batch processing is a special case of stream processing. Oh, hello. Sorry, the light's in my eyes.
Say that I wanted to, with your orders topic, I wanted to omit an event after I saw 10 orders in an hour. The way you described it, I would only get that after an hour when the window closed. What if I wanted to know as soon as that 10th order landed? Like, can I get something to do a count and then to tell me when a threshold has been hit?
Yes. So I don't believe there are any out of the box window implementation to do that, because I've been thinking about a similar thing. But you can implement custom. A window is essentially you can implement a custom trigger and a custom process function. So you can define that yourself, but you would have to write the code that does that calculation.
So that takes me out of SQL. I'd have to do Java to do that?
I believe so, yes. Correct me if I'm wrong, anyone. Yeah. That being said, we could add something like that. This is obviously an open source project, and contributions are welcome. Yeah. Cool. Any other questions? Okay, thanks. Feel free to come and see me afterwards if there are any more questions. Thanks, everyone.